Each year in this country, we spend some £35 billion to buy energy for use in homes, in buildings like schools and hospitals, and in office blocks. A large part of this huge bill pays the heating costs. The problem is that much of this heat energy is wasted. Heat is transferred straight through the walls and roofs of the buildings and warms the air outside. This aircraft is fitted with equipment to search out those buildings that are losing heat energy to the outside. Aerial photography uses cameras and film sensitive to light. Aerial thermography detects infrared radiation, heat. The surveying crew will collect their data at night. The engineers need to be sure that the instruments are detecting only heat energy escaping from buildings. Infrared detectors would also register the sun's energy, reflected back from the ground. The most accurate surveys are carried out on a cold night, with little cloud and no wind. At first glance, the infrared image looks very like an ordinary photograph. But this is a record of heat radiation, not light. Now, Nick, what are you looking at?
This is the thermal image of a factory. We're looking down from the air onto the buildings here.
Right. And what are the different shades of grey and show?
Yes, the image is made up of varying shades of grey from black through to white.
Yeah.
Black are areas of low temperature, and the warmer the temperature, the lighter the grey colour.
Right. Can you do it in colour?
Yes, it shows up better if we do it in colour here. So we can choose the colours. We'll start off with black. Dark blue. Purple.
Those parts of the factory that are at the same temperature are shown in the same colour.
Green.
The difference in temperature between differently coloured areas can be made as small as 0.2 of a degree centigrade. 1 degree centigrade is more usual. What do you learn from looking at an image like this?
Yes, we can see an obvious area here of white heat loss, which we can zoom in on. You can see the white underground pipe here, which is obviously losing heat, which is hotter than the surrounding areas.
And can we look now at the roof of the factory over there? I can see some hot spots there.
Yes, this is quite a warm building here. You can see the lighter areas along here. That's probably heat loss through vents. It's difficult to know until an on-site investigation is made, but the energy manager could investigate the matter on-site.
Aerial thermography helps to track down those parts of the building where the heat insulation is inadequate. Infrared detectors are also used to search out areas of heat loss from houses. This camera is detecting the heat energy radiated from the walls, windows and doors of this house. A camera that records visible radiation sees this. The infrared image shows the hot centre of the chimney and the high air temperature at the top. This is the flue of the central heating boiler. The flue is extremely hot, and so are the bricks around it. The glass in the windows conducts heat better than brickwork. But the thermal image also shows the heat loss through the brickwork, from the radiators inside the house. Heat energy is lost through the glass and the metal frames. But less heat energy is lost where the curtains are drawn, on the right and left of the glass doors. The problem is, how can you reduce the amount of energy that is transferred from the inside of the building to the outside? All new homes will have certain basic insulation systems. New houses are built with cavity walls. That's 2 layers of bricks with an airspace in between. The inside layer is built with highly insulating thermal blocks. All new houses have to be fitted with a layer of insulation in the roof, and that layer must be at least 100 millimeters thick. That blanket traps a layer of still air. Now, still air is a bad conductor of heat. And so, the heat energy stays inside the house. It isn't transferred through the ceiling and into the roof space. And these windows have 2 layers of glass. The 2 panes trap a layer of still air, so the heat energy stays inside the house. It isn't transferred to the outside so easily. All those insulation systems can be fitted to new homes relatively easily and cheaply. You can add insulation like this to existing homes. The question is, how much will it cost and how much will it save? How long will it take to get your money back? You can stop the loss of heat energy by putting insulation between the inside and the outside of the house. What you save on fuel bills depends on the type of house and the type of fuel. Let's try a semi-detached house with gas heating. Insulation in the roof will save around £65 a year in fuel bills. Adding insulation to the walls saves another £65, and double glazing £30. But there's a problem. Roof insulation may cost only a few pounds. Double glazing can cost thousands of pounds. To save money on fuel bills, first you have to spend money on insulation. These houses are used for testing systems of insulation. In fact, nobody actually lives here. These houses are experimental houses. Each house uses energy for heating and lighting, just like an ordinary house. Curtains open in the morning, just like an ordinary house.
2 minutes to 8 now.
And because humans give off heat energy, they need to be represented by 100-watt light bulbs. Light bulbs switch on and off to represent people moving from room to room. Heat energy is lost whenever the front door is opened. Here, a fan switches on and sucks out warm air. Day after day, this house models the energy use of an ordinary, average, semi-detached house. And it does this quite automatically, under the control of a computer.
And here is the host of Blockbusters, Bob Homer. Thanks for being with us.
The important thing is that this semi-detached house has one just like it next door. Both were built in the same way, and both experience the same weather. Certain types of insulation can be fitted in one house, but not the other. And any difference in the fuel bills will be because of the difference in insulation. This fan is sucking air from a house. That air will be replaced through leaks and small cracks all over the building. Some drafts are necessary to carry away stale air and moisture. But there can be too much ventilation, too much cold air. Thermal insulation and draft proofing are two ways of cutting down fuel bills. Most houses get their heat energy from burning coal or gas or oil or by using electricity. And you pay for that energy in the quarterly bills. But some energy you can get free. These houses were designed to trap free solar energy. The problem is, how can you trap energy from the sun? Dr. Yesh, can you tell me a little bit about the background to designing houses to trap solar energy?
Solar energy is available to all houses, and it is the most natural source of energy to use to create a good environment. Through intuition, the Victorians knew this very well, and they built conservatories attached to the south side of the house, because it is in the northern hemisphere, the south side, that gets most of the sunshine.
What happens if it gets too warm?
If it is too hot, as it does get here, sometimes 31, 32 degrees even in the winter, we have movable shutters in order to control the incoming energy, as well as we have louvered windows which bring in colder, fresh breeze from the outside.
The sun itself helps to control the heat energy absorbed by the building. In the summer months, the sun is high in the sky. Only the conservatory and a small part of the interior of the house absorb the sun's energy. In the winter, the sun stays lower. Now, the sun shines into the building itself. The floor and parts of the wall retain the sun's energy. At night, this energy helps to keep the building warm. In practice, solar houses may look only a little different from traditional buildings. Large windows on the south side let the sun's energy into the house. The radiators are small, and small windows on the north wall lose only a little heat energy through the glass to the outside.